Here's what IB expects you to know in terms of static electricity, also sometimes known as electrostatics. And so here's what IB expects you to know about static electricity, or electrostatics. Our discussion of electricity, we're going to start with electrostatics. You should appreciate that there is a force between electrical charges. How do we know a force was being exerted here? Because something moved. Thank you very much. Excellent. Remembering that forces are vectors, you should be able to describe, compare, and contrast the method of charging something by friction and by induction. Okay, sometimes this method by friction is called conduction. We'll talk about that too. And then understand and explain the use of an electroscope. This little device right here is called an electroscope. There's another one that's slightly different in design, but acts the same way. So electrostatics, what does static mean? We talked about static friction. It's not moving, okay? Static electricity is electricity that is not moving, stationary, not flowing. Once we get into electricity that's flowing, we will call it current electricity. And that's what you plug your things into, electrical currents, right? And that can be dangerous. Static electricity can be dangerous, but generally it's not, because it's not usually that strong. But let's go to this idea about forces. In the realm of physics right now, physicists tend to believe that there's 4 fundamental forces in the universe. What's the first one that we've already studied? Gravity. We talked about it extensively last semester. Hopefully you have a decent understanding of it. It is an attractive force between masses. The next force, the one that we're going to study now, is electromagnetism. Okay? Much stronger than gravity. Okay? Weak nuclear force and the strong nuclear force are the last 4. Or the last 2, I mean. The last 2 of the 4. It turns out that recently there have been discoveries that cause physicists to recognize that the weak nuclear and electromagnetism are in fact, why is this not working? Are in fact the same force. And sometimes this is called the electroweak force. They are no longer the same in this point in the universe, but way back right after the Big Bang, they actually were unified as one when the energies were higher and things were different. There are a lot of physicists that believe that we should be able to unify all 4 of these forces, but we have not yet been able to do so. Anyway, gravity is the weakest by far. Electromagnetism is stronger. Strong nuclear is much stronger. And the weak nuclear falls in there somewhere, I think, between electromagnetism and strong nuclear. Okay. If I were to ask you, just real quickly, to think of an atom or draw a picture of an atom, what would you visualize? What would it look like? Okay? Excellent. Hopefully, okay? This is what most people think of when they think of atoms, okay? Atoms. And I want you to recognize that this is not a bad idea of what an atom looks like, but it is not truly what an atom would look like if you went and looked at it. I'm not sure. Yeah, you've got electron clouds. You get into quantum mechanics and probabilities. But the basic structure of the atom is something you should have an understanding of. What do we call this part here? The nucleus. What do you find in the nucleus? Protons and neutrons, okay? Protons, tell me about protons. Positively charged. And when you say positively charged, what are you talking about?
Electricity.
Thank you very much. Electrical charge. Excellent. How about neutrons? They have no electrical charge. Interesting, okay? What are these little things that are flying around the outside? Electrons. And tell me about electrons.
Negatively charged.
Negatively charged. So again, they possess this thing that we call electrical charge. So think about this for a second. On an atomic level, there is a fundamental property of matter that is electrical charge. Some things have it, some things don't. Protons have it. Electrons have it, but opposite. Neutrons don't have it, okay? So something about the world, the universe that we live in, is electrical charge. This concept of electrical charge is a fundamental property, okay? And when we charge an object, when something is electrically charged, it has either gained more electrons or lost some electrons. It's gained or lost some charged particles, okay? What else? Where does the mass of the atom reside? The nucleus. Most of the mass really is the nucleus. Electrons are much less massive than protons and neutrons. How about the volume? What is an atom mostly made of? Empty space. 97, 98% empty space. Let's talk about some fundamental properties of electrical charge, which you guys are probably already aware. What is true about oppositely charged objects? They are attracted. Similarly charged objects? They are repelled. Please remember that. Please remember that. That's a useful thing to know, okay? By the way, we call these positive and negative. Why do we do that? Why do we call them positive and negative? It's a good guess. Could be the poles.
Because this is positive.
It was actually Benjamin Franklin. So in the world of electricity, we have things that are conductors and things that are insulators. Give me an idea of something that's an electrical conductor. Water can be. Pure water is actually not. But water that has ions in it, totally. Totally. Copper, very good conductor. Any metal is a conductor. There might be one metal that's not, but I don't know of it. But generally speaking, okay. Insulators, we could look at that. Tell me some things that are insulators. Rubber, what else? Hair, sure. What else? Plastic, sure. How about glass? You are a conductor, but now we're talking about insulators, Omri.
I know, but I missed it.
I know. Okay, thank you. Glass, wood, water, if it's pure water with no ions in it, is actually a pretty good insulator. But water with ions in it is a conductor. Air is a good insulator. What is the difference between a conductor and an insulator? Okay, let's simplify for a second. Rather than explaining why something conducts, what does it mean to be a conductor? Electricity can pass through it very easily. Electricity can flow through it very easily. It transmits electricity. In terms of an atomic level, electrons and protons and things like that, what is happening on a conductor that is not happening on an insulator? The atoms are? The electrons are. So the difference between a conductor and an insulator is that in a conductor, there are electrons that aren't tightly bound to the atoms. They will flow very easily. In an insulator, that's not the case. In an insulator, the atoms are very greedy, and they hang on very tightly to all of their electrons, and they don't share. Okay? So that's kind of, on an atomic level, the difference. Electrons flow. Please recognize that when we're talking about electricity with solid objects, it's electrons that are moving, okay, in electricity. When I have a plasma or a liquid, it is possible to have positive charges flowing as well. I can have nuclei flowing or ions flowing one way. But when we're talking about electricity through solid objects, we're talking about electrons being transmitted or electrons moving. Luke. Now, we've talked about the law of conservation of momentum. We've talked about the law of conservation of energy. It turns out that there is a law of conservation of electric charge as well. And basically, it's the same thing, that charge is caused by separation of electric charge, not by creation of it. So when I rubbed the magic wand and it became electrically charged, it was because it gained electrons. But I didn't just make those electrons appear from nowhere. Where'd they come from?
Separated.
Friction with the fur, and it ripped electrons off here. So if this thing gained 6,012 electrons, how many electrons did the fur lose?
6,012.
That's conservation of charge. It has to be that way. I can't just make electrons appear out of nowhere, but actually, that's slightly untrue. But generally, that's true. Here's where the slight untruth comes in, and this is also a slight violation of the law of conservation of energy. So really, in modern times, in the last 100 years, we recognize that it's the law of conservation of mass and energy, and that can kind of be said for electric charge, because when Einstein told us that E equals mc squared, what he showed us is that energy can become mass, or mass can become energy. So energy can actually be created or destroyed if it's converted into matter, and vice versa. But that ratio still stays the same. There is still a conservation. And the crazy thing is if you have enough energy, let's imagine I have a photon for a second, which is a particle of light, a little piece of light. I have a gamma ray photon, which is very high energy. Thing's got a lot of energy, and it's cruising along, this photon's cruising along, and it's a gamma ray, and it's got so much energy that it decides, hey, I'm going to become some mass. It can do that, and it can spontaneously become matter. But the crazy thing is, let's say an easy thing to become is an electron because it's pretty small. But notice it has created a negative charge when it does that. So it can't do that. So actually, when this happens, a second particle is also created, which is called a positron, which is an anti-electron. And it has a positive charge so that the net charge of the universe hasn't changed. It's still conserved. Okay? It's one of the ways antimatter gets created.